Hi, everyone. Welcome to another Haskell study group. Today, we're going to be talking about building projects in Haskell using Cabal and Stack. And we'll go through a sample project that will end up adding some additional features and things like this to add it to make it interactive, maybe create a small library, and so forth. This corresponds to roughly chapter 13 that's in the Haskell book, and I don't believe either, unless you use real world Haskell. In real world Haskell, I think goes more focuses on Cabal, if I remember correctly. Then learn you a Haskell for the greater good. I don't think covers project building. So this is a particularly unique chapter to this. Out of the books that most people end up reading and learning about Haskell, which I thought was pretty neat. One thing, though, about this book it's a small criticism is although we are going to expand existing functionality, the book mentioned that it would give you a predefined project first, and I think that that's a bit unfair and a bit disingenuous. Like, if you're going to end up, showing people and creating stuff, you should really kind of go through the beginning and make it a proper tutorial instead of trying to do like a Git clone. Now, obviously, I can probably understand that pruning and creating tutorials out of the book and having them separated may allow a book to go under a particular page limit that was necessary. I don't know all the details about why this wasn't focused on that, but when I saw this, I was like, this is something that we can stray away from what the book provides. The book is a basis that we obviously use to drive our discussion. That's kind of how I normally try to teach these things. But to begin with, we'll be talking about essentially what a Haskell project is, how projects are created inside Haskell, what Cabal is, and Cabal is kind of a build system, if you in a way, and how we can leverage Cabal to build modules, particularly single modules. Doesn't handle multi-level modules, and then we kind of show at that point what the use case is for a project like, say, Stack, to create real-world projects and real-world issues. Before we get started in more detail about with our discussion today, a couple announcements. We will be off for the next few weeks, and we will return in the second week of December. December tends to be kind of the time where the holidays are coming in, people are joining with their families and stuff. So just pay attention to our meetup page for announcements if we're going to have potential cancellation due to the holidays. I usually don't know when certain days are appropriate and stuff, and I tend to plan some of those out only after I have more information. So when I know more about schedules and my own schedule, I will mention to the folks that are on our meetup and folks who are listening to the stream, please join the Atlanta Functional Programming meetup for more up-to-date information as to upcoming events and so forth. We'll get announcements out accordingly, and if our schedule stay the same, we'll stay the same. Otherwise, you'll see some meetup cancellations. So get started with talking about what a Haskell program is. Up until now, when we've created files in Haskell, we've kind of seen in Haskell something like this. In our tutorial function, we may have, this top level tutorial file that ended up, defining a module, and this module ended up, just setting up, the obligatory program with main, and our main being our entry point, and we ended up using some of the do syntax, which we'll be discussing later today in today's discussion, just when we start expanding our new project. But this is kind of what the structure of a Haskell program normally is. Haskell programs are normally organized into modules, right? Think like Python modules, and it's very similar in respect. A module will contain all the data types, type synonyms, type classes, any instances that are registered for those type classes already, as well as any values that you decided to define in that given module at the top level, right? You can import other modules into the modules in your program. This is how you end up being able to break up different pieces of your program and structure it into separate modules. And that's how you start, building out the building blocks for larger scale systems. And because you've moved potentially some some types, type synonyms, maybe even type class instances, or even type classes, where the type class instance is defined in your own module, but you are grabbing the type class definition or its declaration from a different module and so forth. In there, you would end up getting only the values that have been quote-unquote exported, and we'll touch base on what a module export is later on in today's discussion. But it's very important to understand what a module is and how you end up using it. We've actually been using modules for quite a bit. We didn't quite know that we were using modules other than in a couple of cases where we wanted to actually use some functionality that was in an existing module. An example of this is I think in previous episodes we've actually talked about like the data module, which contains many different types of definitions and type classes that you could actually end up leveraging, some of which are already included in the prelude, some of which are not. And as a result, you may have to actually import a particular module into your program in order for you to actually use this. I think, actually, come to think of it, we actually have an example of this. It was in when we talked about maybe last week. We had an import. Yeah, this is an example of us actually grabbing a module, in this case data.int, which has its own list of types and so forth. And we end up actually leveraging bits and pieces from that module in the scope of our program. Obviously, having a module like, say, tutorial, as we saw earlier, has a good, nice, definition of a simple program, but it doesn't do much, right? We'd like to be able to do something a little bit different than what's actually in this program here, right? We want to be able to actually compile and execute this. Well, we can actually do that, and what I'll do is I'll probably open up a new window here to our discussion. And what I'll do is I'll show you the directory structure of this, okay? And we can actually talk through and show you what this structure is, and this executable structure. But before we do that, there's a couple of things that I want to kind of focus on when we're talking about writing programs with modules and so forth. All right. These modules, with their exported interface, they create what's called a package. That package ends up being used when the project is downloaded in other projects, either your own or if you open source it, other folks using your library or your application. And ultimately, what's going to happen is you have to create, you can create an executable for it by either just simply, in some cases, just doing a simple GHC, which notice if you don't use GHCI and you're using GHC, you are actually just calling out the compiler. And in this case, it looks like I have to... Oh, right, I forgot about that. One thing to note about this example that I completely forgot to mention is if you are building executables or applications, you cannot actually use, for your top-level module name, the name of a different module other than main. This is what this error is. Output was redirected, but no output will be generated because there's no main module. So here, if I just change this to main, and we then do what I tried earlier, you'll see that we are able to compile main, we're linking it, and it will ultimately end up generating an executable. Okay, so this is without using any sort of package manager or any sort of build system. Okay, this is typically something that you could do. One thing to know about this is of course, for the folks in the audience who are familiar with build systems such as make or automake or autoconfigure, one might run with this and say, okay, now sweet, we can actually go and leverage existing tooling like make and generate a make file that could actually compile all our modules that we've already defined, and we can actually go through and link it ourselves. We don't have to worry about all this other build stuff, right? Obviously, that's not true because while it is certainly true that you could write local programs that leverages multiple modules and probably build them using make in a single fashion, if you suddenly start using things like third-party libraries, then that obviously breaks down pretty quickly, and you may have to create a sophisticated build system on top of that make system in order to actually get your stuff working. So, you're in a little bit of a bind when you end up leveraging and trying to be a bit more intelligent than checking out the actual ecosystem. And that's what the Haskell guys actually ended up encountering early on and kind of solved in the Haskell community. And what they decided was they're going to end up creating essentially a package manager. Package managers is the thing of the day now. Almost every language now under the sun has its own package manager. Some of which might directly tie into the host operating system if you're using a Linux distro. Some may be a completely separate download and package manager repository, like in the case of Golang or NPM for Node. Haskell is no different in that it created its own package manager for Haskell packages, and specifically created something called Cabal. Cabal is the package manager that'll download the interdependencies, but it can also be used to, build some programs. But for the focuses of today's discussion, we're going to be only talking about Cabal as a package manager. And we're going to use for our build system the program that we had you, or the book had us install early on when we started actually reading it, and that is Stack. So what is the difference between Stack and Cabal? First, let me introduce what Cabal, let me talk a little bit more about what Cabal is, okay? We've already mentioned that it's a package manager. As all you know, the package manager definition, a package for a package manager is literally the program that we're building, whether it be a library or application. It includes all the modules defined and declared early on, and the dependencies that you need in order to build the program. Okay, once you have these dependencies, usually a package manager's responsibility is to be able to download these dependencies for the program if they don't exist already on your system, and it will end up using those as part of the compilation process. Early on in Haskell's development, Cabal was created. It stands for actually the Common Architecture for Building Applications and Libraries, or Cabal for short. The main purpose of it is to actually make sure all dependencies for a given module, I'm being very specific of this, all dependencies for a given module are actually available and downloaded, and it helps you to organize all this so that they're all in proper scope when you actually go and build or execute your program. Okay. Cabal mainly deals with packages that have the Cabal file extension. Now I'm trying to find one, if I have one already, so I can give an example of this. Yes, that's right. Okay. So, this is an example of a Cabal file that was created. There's some metadata early on. You can actually go in and look at what the source files is. I mean, don't worry about too much about the metadata and information here in the structure that's here, because we will touch base a little bit more about this as we go through it in today's discussion. But the main thing is that you'd recognize, and I want to mention, is we have metadata at the top, and we actually go down, we define the actual source repository for the project, all the dependencies that may be necessary, like built in the build depends, or even exposed modules in this case, and in the library section. And then obviously we have, in this case, this was a project that actually built an executable. We list where our main module is, and the underlying Haskell compiler will actually go in and deal with all the stuff related to actually building out the application. Up until now, we didn't actually try and build anything. We actually ended up using Stack for this. Okay, Stack is actually built on top of Cabal. So in the end, Stack is still leveraging what Cabal already built on. But there's some important differences here. Specifically, Stack, unlike Cabal ends up downloading its packages from something called Hackage, where you can actually figure out and search for particular packages that are maybe available and get latest versions of them. Hackage doesn't necessarily curate its packages that once they go up into the Hackage search engine. And what I mean by that is there may be cases where you may have a development version of a given package that hasn't been thoroughly tested, already available on Hackage for experimentation. Stack tries to go on the side that obviously for production systems and production applications, it's often the case that unless an evaluation is done, one may not necessarily upgrade the current library of dependency as part of their project, just so that they can consistently build their project. So what Stack did is create curated packages that mirror their respective repository from Hackage in such a way that for a given version, you know that the version that you're downloading from Stack will always compile with whatever dependencies that it may get, or dependencies you may use otherwise in addition to this particular dependency. So you can think of Stack as kind of dealing with the long-term support snapshots of existing Haskell packages. And it does this in a curated fashion, which also means that sometimes certain packages that may be available on Hackage may or may not be available on Stackage, which is the curated equivalent. So I encourage you, when you're looking at packages that you're leveraging, to first determine whether or not a particular package is required or is available on Stackage before you go through. All right. So let's start with working through a basic project. Okay, the way we're going to do this is we're going to first actually create the project. Okay, to create a project, you use Stack New, and if you look at Stack New, you can see that it requires you to provide a package name. It'll create a template from it, and then if you run Stack Templates, you can actually see what available templates are available, as you can see here. And some of the predefined templates include already set up like web servers, like the Rio template is like projects that you may end up using, and each one of them has its own kind of directory structure. So I encourage you to go look at the wiki that's provided by Stack New, as you can see here, and Stack Templates, as you can see here, to kind of figure out which particular directory structure or organizational structure you may want to deal with. For now, we're just going to go ahead and use the default template. Okay. So when we create Stack New Hello with the default template, do I have? Hold on 1 second. Stack New Hello. Following parameters were needed. Not provided. Oh, okay. So I had to give author name. Okay. So when we create, so let me just look at Stack New again. So I need to provide package name. Okay. So let me deal with providing this manually here for now. For those who want to do this automatically, you could just simply do what this is suggested here. When you first load up Stack, you have this thing generate what's called a config.yaml file, and in here you can actually go and specify all the different specific values that's necessary by Stack New to just simply do what I did, which is provide a project name, and just it'll grab all the rest of the information. But here, since we need to provide this information, as you can see in this line, you can just simply pass in each one yourself, and it'll work. So here in this case, we need to provide new template, and we could just, for the time being, since we're not going to really not going to be posting this anytime soon, we could just deal with the defaults here, and we can actually go ahead and generate our template. Okay. When we look at the directory, oh, my apologies, I have to go and delete that. What is this now? Oh, Never mind. Okay. I wrote two different Hello World programs. Okay, so we will end up probably moving that over into our things later on. Stack new. Okay. Let's do that. Okay. So when we create stack new and from a template, and we look at what was actually generated for us, we see a couple of things. One, since this is going to be dealing with, again, like I mentioned, Stack is actually built on top of Cabal for generating, for downloading dependencies, especially. It's very important that we end up dealing with we're going to end up generating things that Cabal needs in order for it to build our stuff. Particularly, in this case, we have a Cabal file that actually is generated from the list, and as you can see here, it gave us all the lists related to Cabal. Sorry, all the metadata required in order to actually go and talk to the author of this particular project, in this case your own. You also get this nice way of providing the source repository. This is important, especially when you are registering your packages with Hackage or Stackage, because the source repository, GitHub repository, is typically what's used to actually download the dependencies when you provide them. And then, as we mentioned before, we actually have, a library section here that's generated for the purposes of, any external libraries that you're providing or you're creating as part of this package. Here, in this case, as you can see, we have this exposed modules. The exposed modules is we'll touch base in a little bit. We'll talk about exported symbols that are part of the public-facing API. That's part of what exposed modules is, and other modules, HS-Surster. We'll touch base a lot on this structure here in a bit. Of course, we also have as we saw before, the executable section where it takes in our main module to know what to compile. And as you can see here, because of the directory structure, we also have source directories also provided in this particular case here. One thing to note that's useful to know is the Stack new template actually also includes as part of its the Cabal file the test suite. This is obviously going to allow us to write unit tests or even specification-based tests. Eventually, we'll talk about different kinds of testing libraries as we go more and more into this discussion. But for the time being, just know that if you want to write tests, there is a generated file already available, and Cabal is already set up if you use Stack to actually go in and build out the tests. The next thing that we need to touch base on very quickly are the two YAML files here that are particularly specific to, I think, Stack. This one is the first, the package.yaml file. Again, this is kind of mimicking and mirroring a lot of the stuff that we saw in hello.cabal. In fact, I'm pretty sure you'd want to actually edit this file, not necessarily the Cabal file, but you'd want to go and double check that. As you can see in here, it talks about some of the generated things related to metadata regarding publishing your package and things like this. And then obviously this is where your compiler options are part of. It's going to be created as part of this. The dependency list here is talking about actually the hello module that is actually available when you go and look into, I think it's actually in lib.hs. Let me just do this, sorry. Some function IO, some function, okay. And if we go and look at, if we look at app, you'll see, sorry, go app. Here we have our main file. And what our main file is doing is importing the library that we've just built and our create some sort of function associated with it. Okay. So when you create a stack package, just to review, you end up getting essentially a source directory created, a test directory created. The test directory contains, obviously, sorry, let's go to the top level. A source directory created, a test directory created in your application directory. The source directory contains your library code. The test directory is going to contain your specification. If we go and look into our specification, and we're going to go and let's just go ahead and go into that. Hello test spec here, and we just do that. You can see that our test is actually set up so that it actually is not actually implemented. One thing to note here, and this is probably important to realize, is when you first set up a Stack project, you may not actually have the version of GHC that the Stack template created for you. So when you do something like, say, Stack build, it may actually do what it's doing now, and that is attempt to actually go and download the latest version of GHC that's specified in your Stack YAML. While this is doing this in the meantime, let's go ahead and actually look at, let me do this, looks like some code is actually trying to download twice. Let's do this. Let me open up another one. Do kill. Yes, Emacs, grab Emacs. Sorry, folks, didn't expect me to do any sort of killing here, but sometimes when you're running this, this can happen. Let's go ahead and do kill all -9 Emacs, and then we're good. And then we can actually go in here and we can start Emacs again. It's going to take a moment because of I'm using Doom Emacs, so Doom takes a little bit to load up and start up. Okay, so back to what we were talking about. So you saw earlier that the let's go to spec.hs for just a minute. Although spec.hs does not have much, it's actually a main module. Sorry, it has a main function. Since you may have noticed that it didn't actually specify a module name. That's because when you are just using modules, okay, and specifically when you are writing tests, which ends up using modules, Haskell has some interesting magic that happens behind the scenes that recognizes that this is a spec module, and it will attempt to actually take the module name that you provided as part of the project description to actually go and build this up. I think it's actually part of the Stack infrastructure. If we go look at the YAML file, as we will in a moment, you can actually see this here in Stack. Sorry, not this one. It would be in hello/package. If we go and look at the tests, you can see right here, we've actually specified the name. It recognizes this as the main module for the executable for the test. So because of this being there, you don't necessarily have to export main. If we actually go and look at also the main as provided in app, pretty sure, yes. Because this is an application, this needs to actually have a main so that Haskell can do some additional things to actually go make sure that the application's type checked and ready to go and may do different optimizations. That piece there, I'm not entirely familiar with. Just as I've been going along, I just kind of just use Stack the way it was. And for the time being, you really don't need to necessarily recognize a lot of the options. Just know that they're there. And this way you can actually go in and change accordingly if you decide that you may want to actually get a particular library that you wrote out into the real world. Sorry, no, we don't want to do that. We want to first let Haskell do its crazy thing, and then hopefully I have enough space. Yeah, we do have more than enough space. Always have to double check that sometimes because one thing about Haskell, well, Stack that I must forewarn most people. If you don't specify in your Stack template an argument of a particular version that may be available on your system, it's going to attempt to do what what's doing here, which is grab the last blessed version of GHC from Stackage, and it'll go in and now unpack it and install it on your system. This is particularly important because if you are trying to, say, target a particular version of GHC, being able to specify that, it would be very useful. And in fact, if we go and look at I think it's in here. Yes, it's in here. So if you specify here the version, and in this case, the version is specified by something called the resolver. The resolver is actually indicating to Stack what version you want to target. It will then go do its best to actually go and download that version from Stackage. For those who may be wondering how far back Stack may provide a particular version, I encourage you to actually go look at the website stackage.org for more information, just mainly because since it's managing multiple versions, I don't know if they're always keeping, since they're beginning every single version that they're of Haskell, just because Haskell always comes out with a new release as quickly as possible due to the active community. It more than likely might be the case that it's more likely the case that they are end-of-lifing and actually deprecating specific resolvers, just so that they could save space once something gets so outdated that it's probably deemed a hindrance to actually allowing these particular things to these particular versions to actually exist. It might be a bad idea to actually keep them around. Okay, so we now have our stack version unpacked. So what we can do is we can actually go into main, and we can attempt to actually start up stack REPL. As you can see here, it's going to be, you could also try doing this directly. It looks like there was an issue actually downloading. Stack error encountered. Let me just quickly do this. Let me go into ~stack programs. Let me do this. Let me take out UHC 8.10.7 and have it do what it should do. And let us go into here, UHC 8.10.7.temp, and let's go ahead and remove this guy as well. And let's run this command here. And ideally, this should actually generate what we expect it to do, but we will see. Come on. UHC 8.10.7. Let me just do this again, because I just realized that we're not getting verbose. So I'd like to be able to actually see that we're actually getting some stuff out as expected. And then ideally, once you unzip this should all just kind of work. Sometimes you might end up encountering this one thing, so it's useful for us to actually go through this exercise of exporting. It's going to take just a few minutes. So I'm just going to let it do its thing here. In the meantime, let's continue our exploration of our actual package that was generated by Stack. So we talked about the app, source, and test directories. The one thing that we haven't touched base on is this one interesting file here. This one is mainly to set up your package for distribution. Because it is an application, this will have the main function being the default main, things like this, and you'd be okay. Give me a second here. Looks like our good friend Emacs was having some trouble. with the fact that we had a failed process, because sometimes if you're using Doom Emacs and you're downloading some stuff from Stack, I have seen this happen before. When you run Stack REPL and it can't find it, it'll start failing, and then it'll keep on retrying until you quit the process. So that's a problem with the package that I'm using for Haskell development in Emacs. Specifically, it's called Dante. But those of you who are using other ones, you might actually encounter the same thing. So keep that in mind when you are actually leveraging Emacs for Haskell development. Okay, let's try this again. Software package, Haskell, hello. Okay, so we've covered, I think, the majority of the packages. The one thing that I think is important to actually know is this lock file here. This is what's ultimately used to grab specific snapshots and then set them up. Because once it's locked in, and it's generated by Stack, this file is what's used by Stack. It takes in the Stack YAML, your package YAML, all your dependencies that you've provided, and creates this file for use to get the curated libraries it needs to actually do its job. You don't want to, as the message states, edit this file yourself. You want to actually let somebody else, and specifically Stack, edit it for you. You want to edit this, and you want to edit, obviously, either package.yaml or hello.cabal. Okay. So again, hello.cabal would be useful. And actually, you don't. It looks like you don't want to even you do not want to actually edit this file. I just noticed this comment here. So this is actually generated from the package.yaml. So all you want to actually edit, I keep saying quit. All you want to edit is actually package.yaml, which obviously has everything that the Cabal file will have. And in addition to that, if you're dealing with multiple files, particularly the version that you're dealing with, the libraries and package dependencies for multiple projects and multiple modules, then you'd want to also edit stack.yaml to actually go deal with that. This is particularly going to be useful for us when we start encountering dependent packages that we want to actually download from Git. But for the time being, we're not going to actually have to worry about that. Okay. Let's double check this. Okay, got it. Let's move this guy to the top level. Now we have it. Okay, so let me see if I can do this. If I did things right. Let's do this. App main. Good. Okay. Attempts starting the Stack REPL. Let's see if let's even try this here. Software Haskell. Okay, hello. Okay, and we do Stack REPL here, and we should get the same. Ooh, it did not even recognize that. That's interesting. There we go. Oh shoot, doing it again. One of these two is, what's happening is both of them are trying to write to the same files, and that's just going to cause all sorts of havoc. So let's just wait until this is done. Actually, let's abort this. Let's first go into stack programs. This, okay, and let's just remove this file, and let's just allow. Even though I did this already myself, it looks like it's going to try and do it. It's trying to do its best to be intelligent about this. I have no idea why I'm getting this weird error. Oh, got it. RM GHC 7 tar whatever. This guy. There we go. And it looks like there's a file here that okay. Let's screw this up. Let's do this for the time being. And let's do this. Stack programs. Okay. So you can see nothing there, and you can see that. Okay. The one thing that we did not see that the book mentions, that I'm just going to tell you, that when you're using Stack, uh, especially when you're starting new projects, you will you may see this. When you download other people's projects, you may see this. It might complain that GHC is not installed. And the reason for that is Stack sometimes may be configured in the Stack YAML file that to not actually download the latest version of GHC for you automatically. You may, unless the user, you explicitly ask it to. So in cases where you might end up getting a build error, doing a stack setup, all right, and I'll show this to you. Doing a stack setup might be useful to just be aware of. So this can actually then do whatever it needs to do to set up your project. Okay, so if you do stack setup, it's going to try and attempt doing some of the same things that's happening when we try to do a stack REPL here. Specifically, it will attempt to try and download, install, move whatever it needs to do to the appropriate places, and once all that's done, it will attempt to actually start it up in this particular case. Excuse me. So just be aware of that. That's something that that's particularly important to be aware of. If you need to do a stack setup, you can certainly do so. Okay, like this. Now, one of the main reasons why Stack might end up having to do this, another reason, is also is it might want to try to intelligently figure out if you already have a compatible version for the existing libraries and dependencies that Stack needs to actually download. And this is all part of the Stack YAML file that we saw earlier. If we go and look at, I could probably do it here. In the if we look at the Stack YAML file here, you may have recalled that we have this dependency list that we can actually go and look into. That's something that is used by Stack to actually go in and download, like these packages here. It might allow you to download those particular packages for a given reason. Sorry, not a given reason, a given version as specified by the resolver. Now, the resolver syntax here that you're seeing for its Stack, this here is a default snapshot that gets updated all the time. So if you end up having this in every package, you're almost always guaranteed that it's going to assume that you want the latest and greatest of Haskell. So for those of you who are developing large-scale applications or thinking about developing large-scale applications in Haskell, I implore you to figure out what version of Haskell you want to stick with. Find to see what the resolver name is for that in Stackage, and update the resolver from this raw GitHub user content.com URL to something that is can easily be used by Stackage to go and then download the appropriate dependencies. This is going to save you a lot of time and grief, and more importantly, when you are releasing production code and your version is okay for a while, Stackage can actually do the rest for letting you know that the compiler is out of date or whatever. It will figure out what's necessary to actually make sure your version, your software specifically, can always compile with Haskell. So what this is now doing here, and folks who are looking at this, wondering what it's attempting to do is once it unzips the file, it attempts to quickly, and this is on Mac, as you could probably tell. This is because of the path name that's being provided here. It will actually go and figure out what particular symbols are needed from the dilibs, and will actually go and install it in the actual location that we saw earlier, specifically in, if you look at CD stack programs in x86 OSX, these are all the versions that are available. And we can see here that 10.7 is already kind of installed as it's been going through and downloading it. Once this is all set up, when you run stack REPL on your project, it's going to actually automatically just do a quick lookup to see where it is and then run it. So as you can see here, now that we have everything installed, it's going to attempt compiling everything, compiles our main function that we have, compiles the actual distribution, which is the stack setup shim, linking all of that stuff, and then once they're all generated, it will now load those into our REPL, and as you can see by our REPL star main lib pats hello, that's actually our modules all loaded into the REPL. Our module hello, pats hello is the name of the library that's been compiled by the stack setup shim, and the library that's used by main is actually directly used by which is lib, is available as well. Let's quickly just take a look at our stack build and what the difference is. Since we've actually did a build earlier, you're going to end up getting the same sort of like things here. But let's do I think I can actually do a clean just to get it started. Yeah, stack clean would be much more useful. And let's do a stack build again. When you run this and you do a stack build, it's going to create something called a dist directory here. I think it's actually stack work. Yeah. The stack work is your workspace's local distribution with all the necessary builds. It will also include, I don't remember what this DHCI directory holds. This is probably just cached object files. It's Cabal's related things. So when it downloads, Haskell actually requires you to actually do some stuff for Cabal to actually do its magic. And these are all the macros that are leveraged by Cabal. Specifically, it's taking stuff related like major, minor versions because Haskell packages use semantic versioning. It keeps all that in and generate them from the package YAML so that you just, when you compile your code, you can actually directly compile your code without having worries about passing in all that information. The other thing to note about this is the dist directory here. The dist directory is ultimately where your artifacts are going to be held locally. So in this case, we create this Cabal directory, and inside Cabal we have our build directory, which actually holds our artifacts that we created, specifically the pats hello library, the executable, but the executable for hello is actually located in hello-exe, and then our libraries modules are object files, as you can see here. Now, there are a couple of other things in here that you don't necessarily need to worry about, primarily things like setup configuration, things to talk to the stack, and talk to Cabal and things related to setting up the final distribution package. I encourage you to actually explore this directory structure. Some of the generated things are pretty neat to go and take a look at. But the real meat of it is when you're ready to actually go and distribute, we already have kind of a version of your exe already packaged and ready to go. Okay. So you could certainly just use this to actually create your final installs, things like this, if you're obviously installing this on a desktop. Or you could take this directory structure and then use this as the basis for writing a installer for your distro of choice. Or if you're on Windows, writing a chocolatey script, or using NuGet to write for your application. I don't know if NuGet allows you to deal with Haskell installations, but I encourage you to look at Chocolatey. I've used it to actually download some other stuff, and that's kind of one reason why I'm mentioning it here. There are multiple package managers available for Windows that you could just take a look at. And, if you're familiar with one of them and you want to just distribute on that one, you'd have to write out whatever particular script you need to do that install, and you could just use this directory structure as is. Now, the astute viewer would recognize that while we have all this kind of available to us at our disposal, we can't necessarily just run hello here, or even \hello like you would, because the artifact, the actual executable, doesn't actually exist at this level, in this path, right? But the fact that we have Stack with us doesn't mean we can't actually run it. Stack has something called the exec command that allows you to look up whatever package that's defined in the YAML, and it will actually go and execute it. If we look at this command, you actually have to specify the name of the command, the name of the actual argument or command that you want to actually run. So in this case, what we could do is we could leverage this and just run hello, and it will actually go in and, sorry, it's not hello, it's called hello.exe. Let me go and correct that for a moment. Give me a second, because I really don't like the fact that this is called hello-exe. Oh, sorry, wrong one. It's going to package.yaml, and this is just going to be called hello. Okay, let's just do, oh, sorry, that's not what we do. Okay, now let's just do a stack clean. We do a stack build. This is just going to be the same thing that we had before. Now, let's go ahead and run exec-hello, and we'll get our actual name called sumfunc. And if you recall, in our library here, defined in our source directory, sumfunc is the name, we're just returning, we're just doing a put string line on sumfunc here to actually go and execute. All right. So a couple things about this that I'm just going to mention here. Sumfunc is a function that's actually part of the public API. This is specified when you are defining the module. You can create these additional, well, you can add these parentheses between your definitions and your name of the module, and this is where your exported symbols or exported module exports go. Okay. You could certainly empty this, but by doing this, let's see what happens if we do this and have something like this. You're going to see very quickly that you will get a build error. Okay. Because we actually did not expose that. So by doing this and actually exposing it, we can actually go ahead and link everything together. Okay. Let's add, another example. Since we didn't actually generate this, we can actually add, yet another name. Let's do this and just do the same thing that we defined here earlier. Another function called. Okay. And here, what we'll do is we're going to go ahead and update our main function, but we're going to actually do something a little bit more interesting. We want to run these things in kind of like sequence. Okay. Actually, before we do that, let's. I'm jumping ahead. Let's just quickly touch base on one thing that was automatically generated for us, but we haven't really discussed too much, which is what exactly this library stanza is in the hello.cabal, because this is going to be needed later on when we start talking about imports. So it's useful to know that this library let's go back to the package. Okay, this library function here and these dependencies are all combined to creating essentially this hello.cabal file that ended up creating this section here. Okay, this is taking in our source code, whatever dependencies are required. What is the base Haskell version? I think it's part of the base library, but I don't remember right now. And what this does is allow us to actually go in and create an actual artifact called things. Once we've actually named this, and let's call this hello lib, all right? Actually, since I have to go and change this, I would have to go and change source lib this. And let's call this guy here hello lib, okay? And let's go ahead and I know I'm just usually you'd want, rule of thumb is that your name, the module name should kind of match the name of the file that you provide. I haven't heard anybody say that you could split modules across multiple files, or I have not seen that. I think in general Haskell follows the same rule: single module, single file. If I'm wrong about that, please correct me. I haven't seen anything in the book that mentions that otherwise, so that's kind of why I mentioned it here. But since it is single module, single file, you want to kind of name them the same thing, so that way you don't have to go hunt down where a module is actually defined. But for the sake of simplicity, so that we don't have to go through and do some file operations in real time, I'm just going to go ahead and do this. Now that I've actually defined this, I'm going to actually go ahead and leverage in our package.yaml. We want to actually provide oh, it's probably going to generate that now before I actually go and do this. Let's see. Stack.build. If I go and try to do this, is it going to find it? No. Okay, file name does not match module name. That's what I figured. So we actually have to use this. Okay, so that's fine. That's okay. I thought I can actually go and change it. The one thing that I want to kind of compare and contrast is what is in here and what's in the Cabal file. Okay, particularly with respect to hello and other, the executable section and the source section. So if you look in the actual package.yaml file that Stack is providing us, you have these base dependencies here, and you have these for source code and executables. You could provide the source directories, right, which matches the HS source dirs here. The dependencies creates essentially build depends, which is available in both the executable and library directories. The Haskell 2010 thing, I think, is just a default version of the standard that we're just going to end up leveraging. And then the fact that we listed the dependencies for hello, okay, which is the name of the module that we actually are generating in lib. This gets added into build depends here. Let's see what happens if we actually go and just comment this guy out. Okay, or even just take it out directly, right? So let's just do that, okay? Obviously, I'm not going to leave this as is. If we go and now run stack.build, it's going to attempt to figure out where hello is. Hello doesn't actually exist, and now we can't actually import it anymore inside the module. This is something that we kind of expected, right? But you can also see that hello.cabal gets updated automatically. It generated a new hello.cabal, which explicitly says that we don't need to depend on hello. So the hello library that we're creating actually has now become completely hidden. That's what that means here. That's saying that, you know, it's a hidden package that's being created, okay? So let's go ahead and change this back. This will automatically see that when you go into this, it will update the code here. When we do this, hold on 1 second. Cat hello.cabal. Yeah, it does exist. Weird. Why did this not get updated? Oh, sorry, I'm looking at lib. As you can see here, it now shows up again inside of our final hello.cabal. So this is the mechanism that you'd want to use to actually go in and set up your package structure. So this way you can actually deal with different dependencies. Let's extend this example that we saw here with adding a library, and we're going to just create a new function here. And we just created this function here called another func, but this is actually not is hidden from us, right? So what that means is if we go in and attempt to say, let's clear this guy out, this window. If we go in and say, attempt to use it here, let's say instead of some func, we want to use another func, okay? Obviously, what's going to end up happening is this will be out of scope, okay? Because another function is not actually exported. But as soon as you end up doing another func and put it in our exported list, okay, we need to add, obviously, a comma here. Now, everything gets compiled, we load it, we're good, we load it, we're actually executing, all right? This is a very important thing to know, just because when you are debugging your log and things, you see variable not in scope, that might more than likely mean that you forgot to actually go and expose the function, all right? We have just seen an example in our generated hello project of a module import as indicated by import lib, okay? As you can see here, we needed to actually import this guy in order to call another func, or even some func for that matter, okay? One thing to know is if we do this, you have that or some func, okay? If we try and comment this guy out, you're going to see immediately an error from your compiler saying out of scope variable is being used, okay? So this is something that you should be aware of. Imported modules, when you import stuff, especially in the REPL, when you're dealing with things at the prelude level, they're considered top-level declarations, which means if there are already, if you are this is especially something that you should be aware of if you are doing interactive development. If you have a top-level binding, all right, of a name, and you are importing a module with the same name, I'm actually almost certain you will actually end up getting a name conflict and will complain. The easiest example of this is, let's say that we had sum function equals 5. So if we actually look at sum function, it's not even a function. It's just, well, technically it's a constant function for those of you who are being pedantic, but it's a value that adheres to the numeric type class, all right? If we try to import lib, and we now do type sumfunc, you will see that sumfunc has not actually changed, but another func is here. So sumfunc has now been prioritized to being the function that you bound at the top level, the declaration that you bound at the top level, and it will not actually import the other functions, which is pretty important to know. If you try to do, I'm pretty sure if I do this is going to complain. Yeah, it complained, but not for the reason that I thought it would. If we go in and instead, start a new sumfunc, you'll see that it's been it will return to its former glory as being the function that was imported by lib. Okay. Let me actually do this a little bit better. Let's just call GHCI, because I have a vanilla GHCI to attempt to do this. And let's see if I can import lib. Will lib show up sumfunc? Nope. So I'll do stack REPL. And I do mine sumfunc here, you'll see that sumfunc is sumfunc. Another func is going to give us another function call. But if I do minus, what was it? Forgetting the command right now. I think it's set minus m lib. There's a way to actually unload a library. I'm forgetting the name. Is it minus m lib? No. It is minus m. Nope. Hold on. That's right. M minus lib. There we go. Now sumfunc should not be defined. No, it is defined. So let's do this. I'm trying to see if I can unload it so it doesn't actually so here lib main and paths hello. Now some func should not exist because it's no longer there. If I do import lib and I do some func, okay, good. Minus lib. Okay, now we could try our experiment. Let's say that we have some functs defined with our standards function, and now let's do an import lib. If I do a type on some func, it will still be defined as the function that we did earlier. But another function is actually appropriately exported. So this is something to be aware of. For name conflicts, especially if a particular symbol exists already in your REPL, it will favor that top level declaration from your imported module definition, especially when the module is loaded. This is very, very, very important to recognize, just because it has implications on now how you end up doing development and some stuff related to. And you can't necessarily do what I was trying to do, which is essentially do lib dot whatever, because that's not. I don't think you can actually leverage that. You could do from lib. Thought you could do from lib import some func, but I don't think that's that. Oh, I don't remember the syntax for that. There's a way of importing a specific thing, I thought. And you can actually see how to do this in if you import lib, you specifically call some func here. Now we get some func. Actually, let me unload lib and let's do import lib some func. And another func doesn't exist, but some func is still going to be overthrown by the one that's already been provided. So that's bottom line is this, the point of this exercise is kind of show you that you have to be careful about your names when you are importing things directly into a particular function. It might be more useful to use this syntax that I just showed you earlier, where you just want to use some subset of those functions, so that way you know ahead of time where your name conflicts may potentially occur. Are there questions? Okay. Let's see here. So at this point, since we have only 15 minutes left, I'm going to stop here, which is essentially section 13.6. Next time, we're going to be talking about essentially how to extend this program to get stuff from standard input. We're going to delve into the do syntax, which is something we've already talked about when we did some simple examples earlier on, but we'll delve into it a little bit more, and we'll talk about I/O. Now, I/O, of course, is going to be our first introduction. We've talked about I/O before into monads, but we're not going to dig too much into it because there's some stuff about monads that you'll eventually deal with when we start encountering that subject, which is going to happen in a few weeks. So be excited about that one. So that's it. We're again going to be taking a break for a few weeks. We'll come back, finish off this interactive programming section to do syntax I/O, and we'll get started on talking about testing, and then delve into our big section, which is talking about monoids, semigroups, functors, applicatives, and monads. The big concepts that make Haskell Haskell. So until next time, I appreciate you all joining me. I hope you have a great evening.